Hi there, and welcome back. So in lecture 11, we're going to start our first application of the integral, and it's going to be on areas and volumes. So in this lecture and in the next two lectures, we're going to be talking about all sorts of methods for finding the area and volume given certain situations. So consider a region bounded between two curves, and we're going to call them f of x and g of x this time. They're both going to be continuous. And we're also going to consider two vertical lines, x equals a and x equals b. So we're going to section this off into some kind of region. And I have a picture ready to go right here. So draw something like that on your paper. So this will be f of x. And then, I don't know, I did something like this. It's not super important right now. Yours just has to be kind of close to looking like that. The really important thing is that you have two continuous functions, and you have a clear notion that one of them is on the top, and then one of them is below that function for the whole interval. And I'll just say this is a, and then this is b right here. So when all is said and done, you kind of have this region here that's sectioned off. It's like this blob right here. And then this is, I'll just call this region capital R. So we have this region here. And in Calculus 1, you start guesstimating what the area is under the curve by doing a Riemann sum. You have these rectangles, and you split them up into a bunch of rectangles, and that's supposed to approximate what the area of this shape is. So we're going to start with that idea. So we're going to consider the Riemann sum. And you're probably happy to know that we're not going to get into too many details with that. We're not even going to do a Riemann sum, really. So you'll probably be very happy about that. But just consider the Riemann sum from Calculus 1. Then we have the areas approximately, and I could take some Riemann sum of this. So I could use maybe this point right here and form a rectangle. And then I could take the point here. And it doesn't matter what my spacing is, if I'm taking a left or right or midpoint approximation. Remember from Calculus 1, you had all these other approximations and such, right? But I'm just going to draw, I don't know, some Riemann sum. And it would go the whole way from here to b. So I'd be considering these rectangles from a to b. And then the width of each of these rectangles would be delta x, and then n would be like the number of them that I'd specify. So the area would be approximately the sum from I equals 1 to n being however many rectangles I choose, and then f of xi minus g of xi, where each of those xi's are these guys right here. It's whatever I'm picking to be my height for each of the rectangles. So this is the height of f, and this is like the height of g. If you take their difference, then that gives you approximately what the rectangle heights are going to be. And then as n goes to infinity, as you make infinitely many rectangles here, the area is exact. And then what happens when you take the Riemann sum, n goes to infinity? We learn in Calculus 1 that that becomes the integral. So this is the integral from a to b of the upper function minus the lower function dx. And this is really the main formula that we're going to learn in this section, is that to find the area between two curves, as long as this one is above this one the whole time, this is how you do it. You specify the interval, and then you do the upper one minus the lower one. Welcome back. So I've moved the area formula out of the way, and I have the three examples that were on the previous screen. So we're going to take a look at all of these. Now for all these examples, and in your future examples for area and volume, I strongly encourage you to take the time to draw a good picture before you start trying to set up your integrals. And the more pictures you draw, the better you are going to get at it. So the first example is find the area bounded by y equals x squared plus 1, y equals x equals 0, and x equals 1. So you want to have a pretty good drawing of this just to see what's going on. You want to get an idea of which function is above, which function is below. That's like the bare minimum that you need to realize for this example. So this is a parabola. So you'll know that because you have the x squared here. If you plug in 0, you would get 1. And if you plugged in 1 for x, you would get 2. So I'm going to plot those points. And I'm just going to use the fact that I know from algebra that that's a parabola. So it'll look something like this. The next equation is y equals x, which we know is a line, and it's actually the main diagonal line right here. This is the line y equals x. The other two graphs are two vertical lines, one at 0, so here's a vertical line at 0, and here's a vertical line at 1. So when you've drawn all those on your paper, you see that I can outline this region right here. This is a region that's trapped on all sides by those four equations. And that's the region that we're trying to find the area of. So the area formula that we just learned on the previous screen, it's the integral of the function above minus the function below. So if you've drawn a good enough picture, you can identify what those are. The function that's above the entire time for this region, the function that's on top, is x squared plus 1. So this is the function that's above. The function that's below, the one that's on the lower part of this region at the whole time, is y equals x. So this would be minus x. So that's how we're going to find the area scanning from left to right. And now we just need to tell the integral start at 0 and end at 1. So those are our bounds for x. So those two vertical lines tell us where to start and where to stop in the integral. OK, and then this is a pretty straightforward integral calculation from Calculus 1. If you integrate all of these, you get x cubed over 3. Integral of 1 is x. Integral of minus x is minus x squared over 2. And you evaluate that from 1 to 0. If you plug in 0, these all become 0. So you just need to plug in 1 and be very careful plugging that in. So you get 1/3 plus 1 minus 1/2. And this is the hardest part of the problem because I have to deal with fractions now. So this is 3 over 6. I'm not taking any chances here. This is 3 over 6. This is 6 over 6. And then, oh no, this is 2 over 6, isn't it? I'm leaving that in the video just to show you that I'm a human too who makes mistakes. This is 2 over 6, right? Because I told you this was the hardest part of the problem. 1/3 is 2/6. 1 is 6 over 6. 1/2 is 3 over 6. All right, now that the difficult math is out of the way, 6 minus 3 plus 2 is going to be 5 over 6 units squared. So we calculated an area. The exact area of this region right here is 5 over 6 units squared. Units squared because it's an area and I don't know what the units are. So usually you're not going to be given the units. All right, so let's take a look at a slightly more difficult example. So now you're going to find the area of the region bounded by sine of x, cosine of x equals 0, x equals pi over 2. Why is this one harder? Well, first, it has trig functions. So that's why it's more difficult. Second, in my opinion, the graph for this one is a little more involved, and you have to be a little more careful. So x equals 0, x equals pi over 2, those are the vertical lines. So I'm going to mark pi over 4, and I'm also going to mark pi over 2. And of course, this is 0 right here. And I'm just going to graph these functions at those points. Again, I need to get an idea of which function's above and which function is below. I feel like I should be crouching down to talk to you here. OK, so the sine graph, this is review. The sine graph starts at 0. And then at pi over 2, sine of pi over 2 is 1. So it would go up to 1 like that. So the sine graph goes like this. And then, of course, it would go back down like that. So this right here, this is my sine of x graph. Cosine of x, it actually starts at 1. So cosine of 0 is 1. And then at pi over 2, this one goes down to 0, like that. So this one is my cosine graph. And now I need the area bounded by these regions. So if you have x equals 0, that's right here. And look that you get this first piece right here that's trapped between all three curves. This is the first piece right here. But what makes this difficult is you actually get a second piece, don't you? Because once you do the vertical line x equals pi over 2, you get another piece. So maybe I should call this one R1. and this one can be R2. So the total area I need is actually both of those pieces. It indeed looks symmetric to me as well. So I could get the area of one of these and then just double it. Hopefully that makes sense. So really, I'm just going to get the area of one of these, and then we'll just double it to make the work easier. So I'll show you what I mean. Let's do the area. We're going to do 1/2 the area. I guess I'll just leave it like that. So the half I'm going to choose is I'm going to do the left half. But maybe on your paper, for fun, you could do the right half. And if we match, then I was right and it's symmetric, okay? So right here, we're going to integrate this first area. So if your drawing's really good, you should be able to identify the intersection here. I go from 0. Pi over 4 is where they intersect. And if you don't believe me, plug in pi over 4 into both of these graphs, and the answer to that is square root of 2 over 2 for both of them. This is the point, pi over 4, square root of 2 over 2. So indeed, they do intersect here because that's the angle where both sine and cosine match. So that halfway point is pi over 4. OK, which function's on top? So cosine is the graph that starts out as above. So it's going to be cosine of x minus sine is the one that's below until we get to that halfway point here. So it's going to be sine, or cosine minus sine on this interval. Let's go ahead and calculate that. The integral of cosine is sine. This is Calc 1 stuff. The integral of sine is negative cosine, but I have a negative here. So this is going to be plus cosine of x, and I'm going to evaluate that from pi over 4 to 0. OK, so if I plug in pi over 4, I get square root of 2 over 2 plus square root of 2 over 2 minus, and you have to plug in 0. Here, you get 0, but cosine of 0 is 1. So then if I put these together, 1 square root of 2 plus 1 square root of 2 is 2 square root of 2, but it's over 2. So I'm just going to get root 2 minus 1. So this is the area of 1/2 of this. So this is the area of the left half. So now to make my life easier, I'm just going to double this. So here I'll say the total area. And you did check this other one for me, right? You did also calculate this one for me? I hope you did. So you should have also got this. So let's double it. 2 times root 2 minus 1 is 2 root 2 minus 2 units squared. This is going to be my total area that's trapped between these curves, because I'm just going to double that. OK, so let's take a look at this last example. So now we're going to find the area bounded by these curves. So we have the square root of x graph, and a line 1/2 x, and a vertical line 9. So all these graphs that we ask you, they're fairly basic. So you should have a good working knowledge of all the familiar graphs from algebra in order to do these. The square root of x graph, if I haven't asked you in class already, I'm going to ask you right now, what's the shape of that? It's actually like this. So let me draw that for you. It goes off like this. It grows faster in the beginning, and then it kind of starts to look like it's leveling off. So this is the square root of x graph. Let's go ahead and mark 9. Let's do that quite far out here, because x equals 9 is a pretty large value. Let's do it right here. This is going to be 9. So there's this vertical line at 9. What is the y-coordinate right here? Well, you plug in 9. And the y-coordinate here is 3. So I'm just drawing enough detail so that when I set up my integral, I know what's going on. So we've taken care of the square root graph. We've taken care of the x equals 9. Last is this line, which I'm going to plot 2 points just to get a good enough picture. The first one I'm going to plot is 0, 0, because that's easy. I know 0, 0 is on this line, because you plug in 0 for x, you get 0. I would really like to know where we are at 9, because that's the point of interest. So if I plug in 9 into the y equals 1/2 graph, you have to take half of 9, which is 4.5. So we have the coordinate 9, 4.5. So at 9, you're at 4.5, which is actually above this. So let's go ahead and modify this a little bit. Put a point here and say that's 4.5. And it's a line, so I need to do my best job, and I'm not a very good artist here. I'm going to do my best job connecting them, just like that. Okay, so now that we've done a good enough job, I'm going to shade the regions that we're interested in. And I say regions because there's two of them, right? The first reason I see trapped between all of these curves, it's this one. It's this pink region. And then they cross at a certain point, and then the line that was the function that was below, it switches to being the function that's above. And then you get this other pink region right there. So do you see the two regions that are trapped between the curves? It's this one and this one. And just like this example, partway through the interval, they switch roles. One of them was above, one of them's below, and now they switch. So we have to keep track of that. And unlike the last one, this isn't symmetric. So I can't do the cute little thing I did last time where you just double it. We're going to have to actually do each piece separately, which is a shame, OK? Maybe you want to pause the video and try it yourself, but I'm going to do it right now. So let's do that. The most important question I have for you is, how on earth am I going to find the spot where they cross? Well, they intersect there, so they have to be equal. So let's set them equal to each other. So this is to find the intersection. To find the intersection, we're going to set radical x equal to 1 over 2x. I'll square both sides. This is going to be x equals, if you square this, so this is what I'm doing, I'm squaring, it's 1/4 x squared. Let's move the x over here, so we're going to get 0 equals 1/4 x squared minus x. I'm going to solve this equation by factoring. I'll factor out an x. I'll get 1/4 x minus 1 if I factored out that x. Now, if both of these are equal to 0, I don't know why I have a double 0 on either side. I don't really need that, do I? We're going to set up two equations. The first one is x could be 0. We already know that, right? There it is. Like, that's the spot where they intersect. We want this one. So what happens if the second factor equals 0? 1/4 x minus 1 is 0. Well, that means 1/4 x is 1, or x should be 4. My drawing's not great because it looks like I'm more than halfway, but this is actually supposed to be 4. So their intersection is going to be 4. That lets us know how to split up the formula. So my area is going to go from 0 to 4 for this first piece, plus 4 to 9 for the second piece right here. We're going to have to split it up because the function that above switches at 4. OK, so let's just set this up for you. Which function is above in the first piece? It's the root function. The root function is the one that's on top here. So this is root x, and then minus the lower function, which is 1/2 x dx. So this gets us the first piece of area that we need. And then I'm going to add on to that the next one, which now you just switch their spots. So the line's the one on top, so it's 1/2 x, and then minus, and then the radical x is the one that's beneath this time. So this is going to be radical x dx. So now from here, I'm just going to do a couple steps to get you a little further along the way, but I'm not going to do all the calculations. You can think of radical x as x to the 1/2, and then do the power rule backwards. So to integrate x to the 1/2, you have x to the 3/2 times 2/3 minus, if you integrate 1/2 x, it'll be x squared. We do the power rule backwards, and then this is 1/4 right here. You would evaluate this from 4 to 0, plus, if you want to integrate this one, it would be 1/4 x squared minus 2/3 x to the 3/2. And you would evaluate this one from 9 to 4. So I didn't have to do too much more work for the second one because I've already integrated these right here. So now you would plug in 4, you would plug in 0. In here you would plug in 9, minus, you'd plug in 4. So after this calculation, you're going to find that the total area is 59 over 12 units squared. If you're not confident on plugging that stuff in, go ahead and finish the problem. Go ahead and try plugging them in and have a nice review of using the fundamental theorem from Calculus 1. OK, I hope these problems were helpful. In the next part of this video, we will be looking at volumes. I will see you in just a moment for that. All right, welcome back. So in this section, we're going to be talking about volumes. And this is just the beginning. And the next 2 lectures, we're going to be learning methods of finding volumes for solids of revolution. But for now, we're going to start with the basics. So cylinders are where we're going to start. So a cylinder just consists of all the points on line segments that are perpendicular to 2 parallel plane regions. And I'll call the 2 plane regions B1 and B2. So here's an example of a cylinder. So again, you're allowed to laugh at my drawings. I'm totally OK with it. So here's a cylinder right here. Please believe me that it is, in fact, a cylinder. And the cylinder has some kind of height here, and then also a base. And we're going to call this R right here for the radius. Now, my 2 planes are the 2 parallel planes right here, these 2 circles, B1 and B2. So it's this and this. And for this particular cylinder, since the bases are circles, we know that the area of each of these is going to be, so the area of the base here is going to be pi r squared. So we know that's true for this. So in particular, like this one is pi r squared, but it's usually a times h, where a is the base area. And the base of a cylinder doesn't always have to be a circle, for example. This is just like the typical cylinder we're used to talking about. But you could have something else as well. So what if you had something like this? You had this one I'm going to call a shoebox. I just have to give you some kind of thing in the real world to help you understand what I'm drawing before I draw it. So this one is a can of some food, I don't know. This one is a shoebox. This time, the base area right here, this one's a rectangle. It's a rectangular cylinder here. So the base area this time, if this is length, this is width, and this is height, base area is length times width. So the volume of this first cylinder, base area, is pi r squared, and then times the height is h. This one, the volume is the base area is L times W, and then h. And cylinders don't just have to look like this. Like now I'm really going to stretch myself here, but like let's say you had some weird blob shape. I'm going to try to identically copy that. Not bad. And then you draw these line segments, all the line segments that connect the 2 planes like at a perpendicular kind of thing. Imagine that's a cylinder. It's like a, I don't know what that's going to be. But you'd have the base area. So we'll just call this one capital A of, I don't know, L. That's just this base area. And then whatever its height is here times h. So this time I can't give you an area formula for the bottom because it's just some weird shape. So this is the nice case. Then the volume of a cylinder is always its base area times the height. What about non-cylinders, though? So we're mostly going to be dealing with non-cylinders. Here's an example. Here's a sphere, or some kind of ball. So suppose we have some kind of non-cylinder. This is also a cone, by the way. It's just laying down. This is a cone. So suppose you have some non-cylinder. If we want to, we can approximate the volume by considering taking cross-sections of the non-cylinder S. So what a cross-section is pretend now this is a tomato. So you have a tomato, you have a knife, and you're going to slice it. And once you've sliced it open, you're going to look at what shape you have inside of it, right? So you have a tomato, you look inside of it. What shape should be there if it's like a kind of like a really nice-looking tomato? It's a circle, right? If you cut into here, maybe I'll draw like a plane cutting into this. So this is like you taking the knife and you're slicing it open like that. And you chop this up, and there's going to be a circle inside. So that's a cross-section when you take a slice of an object. For the cone, it'd also be a circle, right? I'd start slicing like this ice cream cone laying down, so slice it perfectly vertical, and you'd get these little circles that would come out, right? hopefully the visual and me talking about it makes sense. So these cross sections are the slices. You could take n slices of your tomato, and you could have all these little tiny discs that are like lined up. So like, let's say I chopped like a piece of the tomato, right? So then it's like this, and then that. So that's me taking like one little slice of it, right? But I could do n of them. I could keep splitting it up, do like another one, like go towards the end on the right. Here's like another one, right? And I'd have all these different size slices, and they would go like that if I kept chopping it up vertically. You can think of this as a Riemann sum too. It's just in 3 dimensions. But you add up all the little slices, and that gets you the total area, right? So our Riemann sum is going to be the summation a of x of I star times delta x. So delta x is basically how wide am I making the slice of the tomato? And then x of I is just like basically the point I'm picking. So a of this is going to be the area of the base of each of these little cylinders. So all these discs that I'm cutting are cylinders. So a of xi is the area of each of those. And if you sum them all together, you're going to get an approximation for the volume. However, in calculus, you take n to infinity, you introduce a limit, and then suddenly these slices are all super, super tiny. I have the thinnest things, and if you put them all together, that's like the original tomato again. So then the volume is going to just be an integral. So this is the integral from a to b of a of x, where that's the area of the cross section, times dx. So this is my volume formula, just like I had my area formula before. All right, so let's go ahead and draw a picture for this situation. So this is going to be my sphere, and it's centered at the origin. And now what I'm going to do is I'm going to consider taking a slice. And when I cut this like this, it's going to look something like this. You're going to have some kind of circular cross section when you look inside there. You're going to chop that up. And then where I've made the slice right here, we'll call that distance from here to here, x. And then the height of the slice here, this is going to be y. And then from here to here, that's r. That's the radius of the sphere. So from here to here, it's r. So I've made this cut here. Now, to find the volume of the sphere, the volume formula, it's right down there. It's the integral from a to b of the area of the base of the cross section times dx. So here's my left bound and my right bound. So from here to here, this is r. The distance is r. So we actually are going from negative r to r on the x-axis. So this is negative r to r. The area I'm looking for is the area of a circle. So it's pi r squared, right? So I need to figure out what the radius is of this particular cross-section that I took. So from the middle here to the top of the cut that I made right here. So I need to use Pythagorean theorem to solve for that. So we know that r squared equals x squared plus y squared. And then my radius for the cross-section that I took, the cut right here, that distance is y, right? From here to here is y, and that's half of it. That's the radius for this. So the area is going to be pi y squared. So this is the area of this cross-section, and this is going to be dx. However, if you rearrange this, y squared, sorry, this is supposed to say equals. This is the Pythagorean theorem. So if I solve for y squared, I get r squared minus x squared. So then I'm going to plug that in to this formula right here, and I'm going to get r squared minus x squared dx. I'm going to go ahead and I'm going to integrate that. So pi is just a constant. R squared is just a constant. So that's just going to be r squared x minus, and then x squared would be x cubed over 3. And I'm going to integrate that from negative r to r. So then I'm going to go ahead and plug this in. I get pi. If you plug in positive r, you get r cubed minus r cubed over 3 minus, and you plug in negative r for x, you get negative r cubed minus, and here you would get negative r cubed over 3. And if I take care of this, I have r cubed, and then minus a minus would give me another r cubed, so this is 2r cubed. This is minus 1/3 r cubed. If you distribute this one, this is going to be, see the double negative here? You get a plus and a plus. So if you distribute this negative, you get minus 2r cubed over 3. And then 2 minus 2/3, this is going to be 4 over 3 r cubed. So the volume formula for a sphere using this definition over here is going to be 4/3 pi r cubed. You may remember that from like some kind of geometry class or something. But OK, this is just the beginning of our study of volumes. We have cross sections. The cross sections lead us to finding the volume using the limit of the Riemann sums. In the next 2 videos, we're going to be talking about different techniques for finding the volume. I'll see you then.